Welcome back, folks, to our first coding video of writing a convolutional neural network for image classification from scratch. In this video, we're going to write the model class. Before doing that, I have to import the necessary packages, and all of them have to do with Pytorch package. So the first thing I import is the torch itself, and then I'm going to import some sub-modules from Pytorch, and I will call them, basically make a name for them for just easier, for just the purpose of easiness in writing my codes. But technically importing torch is enough, but I'm gonna import torch.nn as nn. I'm gonna import torch.nn.functional as f. This is where all the activation functions are located. I import torch.optim as optim. I'm going to import torch vision dot transforms as transforms. I probably don't need this at this video, but I'm going to import all the torch related submodules, and then from torch.data .utils.data we're going to import dataset and data loader. So these are the two things that we would run this cell to make sure that all the packages are imported. Now we're going to define the model class. So I'm going to start by the class my CNN, and I'm going to inherit from nn.module. I'm going to define the init property itself and some placeholder for any input that I'm going to define for the class. Definitely at the beginning, I'm going to use the super function to make sure that all the things that are defined under the init method of nn module is going to be inherited by my CNN. And right now, this is the time that I will define different components of our model. For the model, what I have decided to put here as a very simple convolutional neural network is to have two initial convolutional layers, and then the output of the second convolutional layers goes into a fully connected layer, and this fully connected layer has is basically the end layer. So the output of those would be the predictions. So whichever number of classes we have would be equal to the number of outputs of the fully connected layer. So in order to do that, we definitely need to define two convolutional layer. I will call them conv1 and conv2. So self.conv1 is nn.conv2d. That's basically convolutional layer. A 2D convolutional layer is defined in Pytorch this way, and the things we need to define are in channels, which are equal to, I will call it num channels, and the number of channels will be one of the inputs of my model, and as a default value I will set the default to 3, and number of out channels is basically equivalent of how many number of channels do we want the output of this convolutional layer to have. And usually this is something that people go with, like 64 channels. So if you think about it, we're going from, if it's 64, we're going from an RGB, which is like 3 channels, to 64 channels. And that's how people define it. You can have different numbers. The more you have, and obviously the more capable the model is to set aside different kernels and create different relations between the pixels. But you also need to take into account that the more number of out channels for a convolutional layer, the more weights and biases the model will have, and the more heavy the model will get. So this is sort of like a pros and cons that everybody needs to take into account. In this case, obviously, I'm going to have this number of out channel as a parameter, and later you'll see I will set it as a hyperparameter. So for now, I will set it as num out channel. And I want one list to have the values of out channels for this conv1 and also for conv2. So I would say the first element of this list would be called here, and I will basically say num out channel, and I will set some default values as 8 and 16 to it, so you can imagine 8 would be here. After that, now what we need to define, and this step is very important for a convolutional layer. We need to define what size is our kernel size, what size is our stride, and what size is our padding. And these are important because these are going to define basically what would be the size of the output image given the size of the input image. So these are important things that we need to define right now. And as for the kernel, I'm going with a 3x3. As for a stride, I'm going for a 1x1. And as for padding, I'm also going for a 1x1. Now, keep in mind, kernel size 3x3, meaning that we have a 3x3 kernel going over. Stride 1x1 means that we're not gonna jump over any pixel. We're gonna take into account all the pixels. And padding 1x1 means that we're adding one empty pixel to the edges of our image. This combination of a 3x3 kernel, 1x1 stride, and 1x1 padding gives you same convolution. And the same convolution means that the width and height of the input image is equal to width and height of the output image. So that's why it's called the same convolution. So at this point, we're done by definition of this convolution. Now I'm going for the definition of second convolutional layer. And in this case, I'm just going to copy things because they are going to be very similar. In this case, in channels are going to be equal to the outputs of the first channel. So let's call this, and the output of this one is going to be the second value in this list. And then kernel size, stride, padding, everything remains the same. Now, keep in mind, with convolutional layers, it's very useful to utilize the max pool concept. The max pool is basically looking at some number of pixels and then decides which one is the maximum value and then only retains that value, and it decreases the dimensions of the image to a decent amount, and this decrease results in the fact that the next convolution layer would have less weights and biases. While we have the most important information carried over, we will have a much lighter model to go forward with. So that's the importance of utilization of max pools, and this is something that we're gonna define here as self.pool and nn.maxPool 2D is exactly what we would like to use. Now, maxPool specifically requires a kernel size that I am setting as 2 by 2 and a stride which defines how much jump we will have, and in this case the stride that I'm deciding to go with is also a 2 by 2. Now the combination of a kernel 2 by 2 and a stride 2 by 2 in the maxPool decreases the dimensions, the width and height of your image by half. So this is something that you can do its calculations and you'll see that's exactly what you will get. And the last layer will be a fully connected layer. That's why I'm calling it FC. And that's an NN linear of basically the number of input in features are going to be equal to, now this is a fully connected layer, so the image needs to be basically lineared and then go into here, and you can basically imagine that whatever is the image height and image width, it is going to be divided by 4, but then it will also be multiplied by the dimension of the last image. So what I'm going to add here is image width being 100 as default value, image height again being 100 as default value, and as for the in features, we're going to have image width divided by 4 times image height divided by 4. This is exactly that, and then this will be times num out channel 1, and that's exactly what we need here. Keep in mind these values need to be integers, hence I will put them in parentheses and then define int and that will do it. Yeah, that's our fully connected layer, but don't forget that we also need an out features, and out features are equal to num classes, which is something that we obviously need to define as an input. And in this case, I put the default value to 102. It could be anything, and 102 is not selected arbitrarily. The dataset that we're going to download in the third video will have 102 classes of flowers, so that's why we have defined it. So at this point we have defined the components of our model, but we have not yet built the model, meaning that these are not yet connected to each other. So the way we define them is by defining a forward method, and forward will have x as the imaginary input, a mini batch of images. Now what I'm gonna do here is that we're gonna say basically we're going to go through the journey of an image as it passes through our model. So first is that, and everything is going to be whatever goes into the happens to our image will be saved in the same memory slot. That's why whatever happens to x, I'm going to save it into x again, and that's a regular practice for saving memory and the speed of training. So x is going to be equal to self.conv 1 of x. But if you think about it, this is a convolution, but no activation has happened here. So what I'm going to do here is going to call the functional submodule under NN, and then also use a ReLU. So this way I'm adding a nonlinear ReLU type activation right after the convolution. So this is going to be my convolution, and then I'm going to max pool everything. So self dot pool of X is going to be reserved into X. So at this point, the dimensions have gone, in terms of width and height, has gone into half. And now everything will be repeated because I have two convolutional layers with two max pools. Remember to put it as a 2. And after this point, we're going to have our fully connected layer. And at the end of this fully connected layer doesn't need a activation. So that would be basically self.fc of an X that needs reshape. And the reshape will be in the form that whatever is the first element of dimension will be the same, because that's the mini batch. We don't want to change that. But the rest will be basically flattened. And at the end, we're going to have X returned. That's great. Let's just test and see whether our model works or not. In order to do that, we're going to instantiate our model, and I'm going to call it a model, my CNN, and I'm going to basically let perhaps all the, I'm going to let all the inputs remains as default values, but I will remember that the random images that I'm making should have the width and height that are defined as input here. And therefore, what we're going to do here is to make some random images. So I'm going to call them X, is basically torch.randn. And basically what we would like to do is to create random numbers as images. So torch.randn, and as for the mini batch number, I'm going to have 32 images of 3 channels, because that should be equal to the num channels. I'm going to have 100 as width and 100 pixel as height. That's good enough for me. And now Y will be my the basically model X. Basically X, if goes through the model, will be Y, and then I would like to print Y.shape. Now if you think about it, the expectation is to have is basically for Y shape to be 32 as the first element of its shape, and as the last element we just need one number, and that should be 102. Let's see if the model works or not, and that's exactly what we get. Instead of getting a 32 by 3 by 100 by 100, the model received this, and output is a 32 by 102 torch tensor. So that's great. We imported the necessary packages, we wrote the model of a convolutional neural network together, and we also tested it to see whether the model results make sense in terms of the dimensions of inputs and outputs. In the next video, we're going to write the hyperparameters, device, model, optimizer, and loss function, and we'll see which parameters we're going to decide to be hyperparameters. I'll see you there.